Log on, tune in, find out. Another good idea from Cambridge.
By Hervé Chauris from École de Paris. And he will talk about alternative formulations to full waveform inversion.
Okay, thank you. First of all, I would like to thank the organizers for inviting me to this nice workshop and to give me the opportunity to give a presentation. So the presentation here is focused on seismic imaging and more precisely around the determination of what I call the background velocity model. So this has been nicely introduced by a number of speakers, by René Edouard, by Wim Mulder, by also Martin de Hoop before. So what I mean by background model, so there is not a precise definition, but at least a background model should contain the low frequency, the large velocity scales, the large structure, the long wavelength of the velocity model. So this is what I call background velocity model. So when you do seismic imaging, you would like to retrieve the Earth's properties, and in seismic exploration, the background model, the velocities vary between, let's say, 1500 meter per second to up to 5-6 kilometer per second. And you may have cases where, in fact, the lower velocity could be even lower, let's say about 800 meter per second or even 300 meter per second in unconsolidated sands. So you may have a ratio of 1:4 or 1:10. So I think there's major difference when compared to what you could have in medical imaging, where you have a lower contrast. So in fact, you really have to do something about what to do with the background velocity model. So a nice way to do that is to use full waveform inversion. So it has been nicely introduced by Wim Mulder on the first day, also by René Edouard. So in fact, it's a general method. It's a simple method in the sense that it simply consists of fitting the data with your computed data and try to minimize the misfit between the two. So it's quite simple, but it faces some difficulties. So through the presentation, through this introduction, I would like to underline some of these difficulties, or to remind now some of these difficulties. And I would like to propose two alternatives, in fact, to go around some of these difficulties. So this is an ongoing work, so I would like to present why these alternatives could be interesting, but also what the current limitations are. So the idea is I'm interested in really the deriving possible modified objective functions in order to retrieve the background velocity model, not the details of the velocity model. The details could be retrieved by the classical formulation, but here more the background velocity model. Potentially would work on a full wave field. So this is more a longer term work, what I would like to go. I'm not there yet. Yeah. So in practice, I will, for example, consider direct transmitted wave field or reflected wave field, but hopefully we would like in the future to consider the full wave field and potentially have a convex shape. So not necessarily convex, but a shape that has, let's say, a single minimum, because we have in practice, as said by René Edouard, to use a local gradient approach, because the size, or by Henning yesterday, because the size of our model is really too large. Well, so that could be some sort of DSO-like approach, so I refer to Bill's science here, and later, in fact, I'm going to explain what I mean by DSO. So this is the second approach. So what is full waveform inversion? It's simple, it's already presented here with different words, so there is an opportunity to maybe to understand it differently, I don't know. Well, it consists, as I said, of minimizing the differences between synthetic shot and your observed shot. So this is, let's say, real data. And what is a synthetic shot? Well, it's simply you model you gather in a given velocity model. So here it's a function of depth and position at the surface. That model consists of a very simple model, single reflector, diffraction point around here. So if you have a source around here, then you could see that you have different events. You have a first arrival, reflected arrival around that interface. And here, this point, we could say diffraction point, acts as if you would have a secondary source around here. So when you model the data, here is for the signal shot, you have receiver position at the surface, and you have time, recorded time. You have different events, and you could easily link these events to the model. You have first arrival here, the image of diffraction point, and here's a part of reflected point. And you may see also multiples in it. Okay, it's easy. Well, when you compare to the observed data, you say, well, it's not exactly what I would like to have, because maybe I have something about the first arrival, but inside I need something more. So I have to have a more complicated model. So probably you have to deal with models like this, and when you propagate this model, the wave propagation, here it's simply acoustic wave propagation, but it's more difficult. You could recognize first arrival, and here zones where you have lower energies because you have some sort of diverging rays, and here you have higher amplitudes, but also behind the first arrival part you have energy, reflected energy, diffracted energy, and so on. So it's a bit more complicated. Well, this picture is about the same as the one shown by Wimbledon on the first day, except that here I do not have any animations. Here I would like to compare in blue a trace. So trace is a record for a single shot and receiver position of my exact data, let's say in blue, and from a computed shot in dashed line. So if I have the correct model, they should fit. If I have an incorrect model, okay, there is a mismatch, and here on the zoom you could see that hopefully I try to match this maximum with this other maximum. Well, with the gradient approach, you will modify maybe smoothly your model, so you will more or less shift this dashed line up to here, but you could also have a model where in fact that one will have a large correlation to another peak. So that's why you have this, when you change the model parameter, you have this nice, or this kind of objective functions, exactly the same. Here I draw it with a pen, but René Edouard presented real ones. Okay, so what to do with that? Well, you hopefully would like to have something more similar to this shape. So full waveform inversion is a nice and attractive method because it's able to potentially deal with a complex model, and it does work on some situations, as explained by René Edouard, under some conditions. And some of this condition has been discussed by Martin yesterday. Most of the time we need to start with a good velocity model. A good thing that you could start, as explained just before, from low frequencies to high frequencies, and it does work on some dataset, on some real dataset, long seismic is complicated, so but it does work as presented here or just before. You may go for other transform. This will be introduced later this afternoon by Henry Calandra, like the Laplace transform. And here I propose two alternatives. Okay, one is a normalized integration method. It's very simple. And the other one is a differential waveform inversion. And I would like to introduce why they are and also the limitations. So the objective is really to get this kind of rayed shape. So, and the objective is, once more, is to retrieve the background velocity model, so the large wavelength of the model. Then once you have this large wavelength, you will jump to classical method to have this nice high resolution reflectivity. So before explaining what the normalized integration method is, once more about classical full waveform inversion, similar to what René Edouard said. So I go a bit fast. I try to minimize the misfit between observed data here and computed data at surface, usually at the top. Well, it's done within 3 steps. First, you propagate your data in a given velocity model. Then you back propagate residuals here. And the residuals here in a joint state method are given by the derivative of your objective function j naught with respect to the data. And then you correlate the two. Here I did it with a single shot, here taking all frequencies together, so I have some sort of reflectivity, okay, and of course I have to add the contributions of all shots. So this nothing special. So I wrote this because the new formulation with the normalized integration method, it's about the same. It's almost the same, except that I minimize the misfit between two quantities, and the quantities is a modification of the data. So instead of minimizing the differences between observed and computed data, I minimize the difference between a modified version. And what is this modification? Well, I integrate from 0 to time of, let's say, a norm of p. So let's say it's a square of p, square of the data. And here it's divided by the same quantity from 0 to the final time. So why the normalization? Simply because for large time, so t equal to large time, q is equal to 1, so I have 1 minus 1. So if I would have added larger times, then my objective function would not have a change. So what does it mean? Basically, I integrate the norm of my signal. So let's have a look. Here I have a trace. So if I record for a single shot, single receiver here, and this is function of time. So it's really oscillatory, and I have a lot of energy at around the first arrival, and then I have a decay, usually decay of our travel times in one of our travel times in 3D. Well, when I take, let's say, the envelope of my signal, so envelope is just the norm of my analytic signal. Here I have only a positive signal, so when I integrate that one, I have a function that is, by definition, increasing with time. Okay, so sometimes it doesn't maybe increase fast, but it's only a function increasing with time. So instead, it's very simple. Instead of comparing oscillatory functions, I compare increasing functions. And the key thing when you have this kind of shapes is that you have a signal with really oscillating functions. So when I compare functions that are only increasing functions with time, then you may expect a better behavior. And in fact, it's possible to prove, the proof is quite simple, that on some simple cases, so it's 2D cases but homogeneous model, and you test different models, that the shape of this function is convex, except maybe close to the solution. But far away from the solution, the shape is convex, and in fact it's quadratic. So, and close to the solution, in fact, you could switch to other formulation. So, it does not mean that for any model it's convex, but at least on simple example. And if you discuss with Bill Symes, then I think he would say that it's very difficult to prove that a function has a nice behavior. Okay, so in fact, you could take, here I use the envelope or the square, you could take in fact any norms and you integrate that one. And to derive the gradient, it's as in a joint state, you simply have, oh, here there is you simply have to derive what is q with respect to here. Here there is a little mistake, because you have the residuals also here. Okay, so let's have a look at an example, very simple example. It's more the transmission case, where I have a shot here and where I have receivers on the other side. And here in black, it's 1 kilometer per second, and here in white, it's up to 5 kilometers per second. And here I just drew some different curves where I change my velocity. So in fact, I change the velocity within the anomaly between 1 to 5 kilometers per second. And here I just plotted my objective function. So in the classical approach, you have this kind of shape, okay, with a number of local minima. And with the normalized integration method, you have here, in that case, a single minima, around here, and you have this nice shape. I skip about the Laplace transform, where also you have this nice shape, and I'll refer to the talk by Henri Calandra this afternoon to discuss this. Okay, so if you do a gradient and if you iterate, so this is on this example, here the exact model is a perturbation of 900 meter per second in the blue section. Well, what you have here is a presentation of a first gradient. I started with an homogeneous model, and what you retrieve with a classical approach is more or less what you have on the edges. So if I go back, so in fact if I have a shot around here and a receiver here, then if I should raise, then you could see I may have a reflection here and here. So in the classical approach, if you take all frequencies at the same time, then more or less you retrieve your boundaries, and not in the not in transmission here. That's why you don't have anything, but more on the edge. With the Laplace transform, so basically you do Laplace transform, and then you play a bit with this damping factor, where basically you deal with the first arrival. Then you have an extremely smooth result. And with the normalized integration method, let's say when I take the power 2, you have an anomaly, it's difficult maybe to see, around the central zone. So if I do a section in this gradient around the middle depth here, I think it's easy to see. Well, not really with a beamer, it's a bit difficult. So you have to trust me more or less. Here you could retrieve the interface, position of the interface nicely here like this. Here you have a smooth perturbation, really smooth perturbation, and for that one you have an anomaly that is flat here, so no anomaly, and in the central part you have this kind of what you expect anomaly. It's very difficult to see on the screen, so you have to trust me. If I do some iterations here with a simple conjugate gradient, then I'm able to decrease my cost function. It takes quite some time, and I could go further, but in fact it doesn't really decrease much later, because probably it does converge to a local minima. Then I end up with about the same, where I could see more or less the edges. If you do the normalized integration method, then in fact it converges really more rapidly. So basically you don't see anything, but the residual has been divided by about 100. And if at the same time I use the same path provided by the normalized integration method, and I plotted the objective function, the classical objective function, what happens is that my objective function, you can't see anything. The classical objective function first increases and then decreases. Okay? So it's a way to grow through local minima. So to conclude on that part, well, I would say that on simple cases it's possible to prove that it's convex. And here it works on transmitted data, because in fact here most of the energy was concentrated on the first arrival. So does it work on more than transmitted data, especially on reflected data? Well, maybe, but it's just a maybe, and this should be further investigated. So this is where we are currently today. So this was the first part of the talk, and second part of the talk is the second alternative. Well, so what I call differential waveform inversion. When you have, let's say for a single shot, you could compute the gradient with a classical approach, and you have something similar to this. It's like migration, I would say. Okay. Then from that one, this is in a model space, you could do some modeling, and you could predict what the shot is, yellow shot, but you also could predict what the next shot would be. So you first do a simple migration for a single source, and this is a key point, and then you predict what the next shot bit is. And then what you could do is that you could try to minimize the differences between the predicted shot at the next position with the observed shot at the next position. And this is written here. So in fact, this modified formulation is done within two steps. First step consists of minimizing for a single source the classical function. it's really difficult when you have the full data, so when you make a summation, when you have a single velocity model for all shots, to minimize that function. That's what has been presented just before. But when you do it for a single shot, in fact, it's quite easy. It's like migration, and you could explain nice details. Maybe you have to iterate, but you could explain all the details. So for a single shot, you first minimize that one, and starting from that model, you try to predict the next shot, and you compare to the observed next shot. Well, so it's maybe difficult, but here, in fact, so you make the differences between predicted and exact shot. What I was able to prove is that that formulation is done in the time domain or frequency domain, it doesn't matter. And this is linked to a formulation in the depth domain. So what is this formulation in the depth domain? I of x is my migrated section for a single shot. If you have a correct model, then you could provide a number of sections depending on the shot position. And for the correct model, they all should look the same, because what you retrieve is a reflectivity, and the reflectivity has nothing to do with your acquisition if the model is correct, except of course on the edges where you have lots of artifacts. But let's say on the central part, whatever the shot position is, then you should have the same migrated image. And in fact, this is the idea of migration velocity analysis. So what you could say is that you could introduce the derivative of I with respect to the shot position, and you say, okay, for a correct model, that the norm of the derivative should be a minimum. And this is exactly the idea provided by Bill Symes some years ago. What is a differential semblance optimization? So here you have some sort of semblance, and you differentiate with respect to the shot position. Here, result is, one of the main results is that you may have a formulation either in the depth domain or in the time domain, and here are exactly the equivalence. The equivalence is through the green functions that make the link between time to depth. Okay, so you could have the same working around a bit on different formulations, and here it's a different image condition. Here you correlate the forward field with the back propagated field. But if you have an incorrect model, you may say, okay, I have the possibility to introduce some time delay. This has already been mentioned by Wim Mulder on the first day. To say, okay, maybe I do not have the good model, so I introduce this time delay. And for the correct model, the time delay should, of course, be 0. So here, this derivative of my image with respect to frequency here is the same as in time domain as being the differences between my exact and predicted shot for the next frequency. So you migrate for all shots, all receivers, but for given frequencies, and then you predict what the next frequency should be. You could do the same with the extended model, where you have an offset in the depth domain. So instead of connecting your image point to the source and to the receiver, then you may have some distances between at the image point, as if you would have 2 image points. Of course, for the good model, then they should all collapse into a single point. And here you could prove that doing this is the same as doing something like common angle migration. Here, where you sort your data not function of offset, not function of frequencies, but you sort your data function of angle. And of course, that angle depends on the model. Okay, so if I summarize, in fact, I have 2 points. First point is that you have, at least for reflected data, you have an equivalence between a formulation in time domain, here on the left-hand side, or in the depth domain. Okay, so for reflected data with the L2 norm, this is the same. But if you do not have only reflected data, maybe it's not the same. So as before, this is just an ongoing work, but potentially in the time domain, you could do more than in depth domain. So for depth domain, you have equivalence, but for the time domain, when you minimize this one, also you could explain multiples. So you will end up with a model that will both explain reflected data and multiples. So probably wrong model, but then you compare and you try to compare with the next chart and you try to have this one. So here you already take some sort into account multiples and then you do the classical formulation. So, but this has to be further investigated. So if I go now to my conclusion, here I have a few minutes to show one example. Okay, so here's an example still where I have shots at the surface and receivers. In the deeper part, I have a velocity anomaly of 600 meters per second, and I started from that model. I just computed the first gradient, and you have images that are similar to the one I had just before. Now you better see the graphs. So here, if I do a cross section at a given depth around here, well, with a classical formulation, you more or less retrieve 80s, as here. And with the other one, you retrieve some oscillations around the 80s, but also what is inside. What is inside could be decoupled into three parts. So term 1, 2, and 3. So why do you have three parts? Because in the gradient you have three parts. Here in the formulation you first have two parts. So you first have to minimize this one, and then you have to minimize this one. So part 1, and for part 2 and 3, when you minimize this one, that one is already, the delta C is already a function of this original objective function. Here you combine, this is a bit written here, you combine two Green's functions. And these Green functions do depend on the velocity model. That's why you have two parts, or two terms. And here, so you have two terms. So here they are relatively different, but they all contain a smooth part or a smooth long wavelength about the velocity model wavelength. Okay, so for reflected data, this differential waveform inversion is the same as the differential semblance optimization as proposed by Bill a few years ago. Here in the time domain, and the original one was defined in the depth domain. So in depth domain, we have some indications that it has a nice behavior. What I would like to go further, not in this talk, but on my work, is it limited to reflected data, and could you handle multiples at the same time, because you have this formulation in time domain. So to conclude, I would say this is really an ongoing work. And I have proposed two formulations. The normalized integration method really works with first arrival, but probably is not limited to first arrival. And the other one works with reflected data, but probably also is not limited to limited data, to reflected data. So this is what I would like to further investigate. And I would like to acknowledge and to thank a number of people. And I would like to thank you for your attention.
Thank you very much, Hervé. While we take questions, maybe we can set up the next talk. Yes?
Hervé, in your first approach, your normalized integration method, if you have multi-event, you will rely on being able to correctly interpret the dynamics of the event. Am I correct?
Yes.
So you will need to have a very precise model of your dynamics, which we have it or not?
Yeah, in practice we do not really have it, because in my case, for example, I'm dealing with acoustic waves. In fact, there are elastic waves. So in fact, when this is true, I'm integrating my trace. So what is key is about the amplitudes, and in fact, what is key is about how much jump do I have on a specific event. Yeah, exactly. So, yeah.
Could you say something about the relative amount of work involved in the differential method and the standard method? The amount of CPU time, is it reduced?
You refer to the normalized integration method? Or?
No, the differential waveform inversion.
Okay, it's more complicated because you have, instead of solving one minimization problem, you have to solve two of them. So, and first you minimize an objective function, and then the result of that one is introduced in the second one, so it's more involved. So it's about twice more expensive.
Okay, so even though the problem's easier, it doesn't converge more quickly.
Yeah, exactly. Yeah.
Yes.
It's also always tempting to transform your problem into other spaces, but as a statistician, you're very concerned about error propagation into your new system. Can you say something about the error propagation when you do the transform in the first part?
Yeah, the first part, clearly it's really more sensitive to noise. So it has been written somewhere, I don't know, I didn't mention, but it's written somewhere. Yeah, it's more sensitive to noise. Why? It's simple to explain. When I have my data, then I take the envelope of the data. Suppose I have Gaussian noise. So the mean of my noise is 0 in my original trace, but it's not anymore 0 when I transform the data,
right.
because I use a nonlinear transform. If I would use a linear transform, then the shape of my objective function would not really change. So I had to use, but I agree, I reinforced noise. Yeah. And this is a key point. Yeah, it's more sensitive to noise. Yeah.
Move on to the next talk. Thank you again, Hervé.